Right now, as you watch this, there are galaxies so far away that the distance between us and them is increasing faster than 299,792,458 meters per second, faster than light, and physics is not panicking. What if I told you there are 3 faster-than-light effects that are real, and one shortcut idea that could, in theory, change everything, except it may require a kind of energy we've never controlled? Stay with me, because by the end of this video, you'll know what can outrun light, what can't, and why the universe guards the speed limit like it's protecting reality itself. Most of us grew up with one clean rule: nothing goes faster than light, and yet the universe keeps producing moments that look like it's cheating. Impossible-looking fact number 1: cosmic expansion can make distant galaxies separate faster than light, not because they're launching rockets, but because space itself is stretching. Impossible-looking fact number 2: some black hole jets appear to sweep across the sky faster than light. If you saw it in a time lapse, you'd swear physics just broke, until you learn the geometry trick. Impossible-looking fact number 3: quantum entanglement gives you correlations that feel instantaneous, like the universe is updating 2 distant locations with one invisible command. So here's the question that makes even professionals slow down. If nature can show faster-than-light behavior, why can't we use it to send a message instantly, cross the galaxy, and basically delete the problem of distance? To understand why this gets so weird, we need the normal rules, the rules that sound boring but quietly run the universe. In Einstein's special relativity, the speed of light in vacuum, c, is not just how fast light goes. It's the speed limit for information and cause and effect moving locally through space. If you could send a signal faster than c, then depending on how someone else is moving, your message could arrive before you sent it. That's not just a mind bender. It's a causality paradox, like the universe letting you reverse the order of events. And this isn't a fragile theory. Relativity is baked into technology. GPS literally needs relativistic corrections to stay accurate. So the speed limit isn't just a textbook vibe. It's part of the infrastructure of reality. But here's the twist people miss. Relativity doesn't say nothing is ever faster than light in every possible sense. It says you can't locally accelerate mass or information through space past c. This is where things get strange, because the phrase faster than light hides multiple different categories: matter traveling through space, a ship, a particle; information traveling through space, a message, a cause; a pattern moving, like a shadow, a spot of light; space itself changing, cosmic expansion. Some of these can exceed c without breaking the rules, but only one would let you do the sci-fi stuff: instant communication, or fast interstellar travel, and that one seems locked. So whenever you hear faster than light, you should ask, faster than light, what? Keep that question in your pocket, because we're going to build the case like detectives, and most FTL headlines collapse the moment you check what kind of speed is being measured. If you like physics explained like a mystery, you can actually solve. Subscribe. What I'm about to reveal is the cleanest way to think about this. 3 real faster-than-light effects, 2 common misunderstandings, and the one concept: warp drives and wormholes that might be mathematically allowed, but comes with a cost so brutal it could keep humanity sublight forever. Stay with me here. Let's rebuild the story chronologically, because the speed limit wasn't invented as a vibe. It was discovered as a consequence. 1905, Albert Einstein publishes Special Relativity. C becomes the core of how space and time connect. 1915, General Relativity follows. Gravity becomes geometry. Space-time bends, and objects follow that curve. This matters because geometry can do movement-like effects without objects locally breaking the 1929, Edwin Hubble shows the universe is expanding. The farther away a galaxy is, the faster it appears to recede. This sounds like a violation, until you realize it's not a ship moving through space. It's the stretching of the space between you and the galaxy. Early 1980s. Inflation theory is developed. Alan Guth is a key name here. It proposes that in the early universe, space expanded incredibly rapidly, effectively faster than light expansion. Again, not because particles locally outran light, but because space itself changed. 1994, Miguel Alcubierre publishes a space-time warp drive solution. The headline version is irresistible. Contract space in front, expand space behind, and a bubble can move without the ship locally exceeding C. Now bring it to the mid-2020s, moving into the 2026 era. Scientists are getting more precise about the only thing that truly matters for legal FTL. How space-time behaves on the largest scales. That's why missions and surveys mapping cosmic structure and expansion. Think the kind of work Euclid is designed for matter. They're not just making pretty maps. They're measuring the arena where the space expansion loophole lives. And at the same time, quantum tech keeps baiting our intuition. Entanglement experiments, quantum communication demos. They keep whispering, "Are you sure information is behaving the way you think it is?" Here's the cliffhanger. Every time physics looks like it found an escape hatch, scientists ask one ruthless question. Can it carry usable information faster than light? Because if the answer is yes, reality becomes hackable. All right, here are the 3 real faster-than-light effects people point. 2, what they are, and why they don't automatically give you a starship. Number 3, apparent superluminal motion, the jet illusion. Picture a lighthouse beam sweeping across distant clouds. The bright spot can move faster than light across the cloud layer because it's not a single object traveling between points. It's a pattern lighting up different locations in sequence. In space, something similar happens with jets from black holes and active galaxies. If material is moving near light speed and angled toward our line of sight, the timing of the light reaching us can make the motion appear superluminal. It looks like FTL, but it's a geometry trick. The particles are still obeying the speed limit. Here's where it gets crazy. It can fool your eyes, your graphs, and your intuition without breaking a single rule. Number 2, quantum entanglement. Instant-looking correlations. Entanglement is the one that feels like the universe is whispering secrets instantly. Measure particle A here, and particle B far away produces results correlated in a way classical physics can't imitate. You might be thinking, so I can send a message instantly by choosing what happens. You can't because you don't control the outcome. The results are fundamentally random. The instant part is the correlation pattern, and you only reveal that pattern when you compare notes using a normal slower-than-light channel. Quantum mechanics allows spooky correlations, but it still protects causality through what's commonly described as the no-signaling principle. Number 1, expansion of space, the legal way to beat light. This is the one that's actually real and actually exceeds EC in a meaningful sense. The distance between very distant objects can increase faster than light because space itself is expanding. Relativity forbids locally outrunning light in your neighborhood. It does not forbid the metric, the ruler of space-time, from changing such that distant separations grow superluminally. Analogy time. You're walking on an airport moving walkway. Your legs have a max speed, but the walkway can carry you across the terminal faster than your legs alone ever could. Cosmic expansion is the walkway. So is there something faster than light? Yes. Space can expand so that distant things separate faster than C. Patterns can look superluminal. Entanglement can look instant. But here's the punchline. None of these let you send usable information faster than C, which leaves the most tempting category, warp drives and wormholes, ideas that try to use space-time itself as the workaround. Alcubierre's warp metric is the famous example. Don't exceed CE locally. Manipulate space-time so your destination comes to you. It's the expansion trick turned into a technology concept, but the satisfying answer immediately opens a new question. If the math allows it, what stops us? Just when you thought you understood, here's the twist. The obstacle isn't imagination, it's energy, and we don't know if the universe lets you pay the bill. Warp drives and traversable wormholes, in many analyses, appear to require exotic energy conditions, often described as needing regions of negative energy density or violations of energy conditions that usually hold in classical physics. In plain language, you may need a kind of gravitational behavior we don't know how to produce, stabilize, or scale. Yes, quantum physics allows tiny weirdness in the vacuum, like the Casimir effect, where boundary conditions between plates produce measurable forces, but turning tiny vacuum weirdness into a stable warp bubble around a ship is like saying a static shock proves you can power a city. And now add the 2026 era layer of mystery. We still don't fully understand the components that shape space-time at cosmic scale. We can measure expansion, we can map structure, but the underlying why is still under active investigation. Dark energy, modified gravity ideas, new fields, multiple models, not one settled story. That's why this topic stays alive among serious scientists and not just sci-fi fans. Because space-time itself still contains unanswered questions. Not anything goes questions, more like the last few percent of the model questions. And that's exactly where revolutionary surprises sometimes hide. So here's the uncomfortable truth. No confirmed experiment has ever transmitted information faster than light. But the universe also hasn't explained every detail of the stage that light travels on. Which means we're left with a real scientific tension. The speed limit seems absolute locally. Yet the arena, space-time, has behaviors that look like loopholes. And we're still learning what's fundamental. I genuinely want to know what you think. If there is a way around light speed someday, which path feels most plausible? A. We never beat it, only get close and accept the limit. B. We exploit space-time, warp drives or wormholes become engineering. C. Quantum reality hides a loophole we don't understand yet. Comment A, B, or C, and tell me the one piece of evidence that would convince you. I'm reading the comments, and I'll pin the sharpest take. This affects all of us because the speed of light limit is the universe's tax on ambition. Even in our own solar system, communication isn't instant. Depending on distance, signals to Mars take minutes. To the outer planets, it's hours. And to the nearest star system, 4.4 light-years away, you're playing a different game entirely. If faster-than-light messaging were possible, it would change everything. Exploration, colonization, even how civilization organizes. But because it probably isn't, the future looks different, and honestly, more interesting. It means autonomy becomes essential. It means spacecraft need brains. It means interstellar missions become long-term projects where time dilation, power systems, shielding, propulsion efficiency, and communications become the real battlegrounds. The frontier isn't how do we break C, it's how do we map space-time better, test gravity harder, improve quantum networks without violating causality, and build propulsion that can realistically reach meaningful fractions of C. The good news? We don't need magic to do epic things. We can explore the solar system with known physics. We can measure space-time ripples from violent cosmic events. We can test relativity in extreme environments. And every year, our measurements get tighter. Science is making progress not by breaking rules for clicks, but by discovering which rules are truly fundamental and which impossibilities were just misunderstandings. But this isn't the only mind-bender hiding in modern physics. Next, we're diving into warp drives in the actual equations, why time dilation is a real cheat code you can't unsee, and quantum teleportation, what it does, what it doesn't, and why it still can't beat the speed of light. Subscribe so you don't miss it. Thanks for watching. The universe doesn't just limit speed, it protects cause and effect. And that might be the single most important safety feature reality has. Stay curious. See you in the next one.